Alright, this is Algebraic number theory lecture 15. So I already started off with a slight mistake. This should really be not integral closure, but integral extensions. So we're going to talk generally about integral extensions of domains. Okay, so let me give you an overview of what the goals are in this lecture. So the first thing I want to talk about are different ways you can describe extensions of rings, but more specifically integral domains. So ring extensions, definitions. So there'll be three important ones for us. There'll be the notion of an extension of rings being a finite extension of rings, an extension of rings being of finite type. So this is kind of bad terminology, but it's standard nonetheless. Finite and of finite type are two completely different, related but different notions. And C, an extensions of rings being integral. Okay. So this is going to be the first section, is just some definitions. The second section is, there will be certain implications between these. So I want to explore that. Between A, B, and C. So for example, a finite extension of rings is always an extension of finite type. The converse is not always true, and similarly, a finite extension of integral domains is always integral. Not every integral extension of integral domains is finite. And the big one is basically integral of finite type. So B and C are equivalent to A. That's what we'll spend most of our time proving, at least in the case of integral domains. So the third is a small thing that, well, maybe not so small. Integral extensions are transitive, so if I have three rings, a sequence of three rings are transitive. So in your head, you should be thinking A contained in B contained in C. If I know these two are integral, that implies that the big containment A contained in C is integral. And I know I haven't told you exactly what integral means, so this should all feel a little fuzzy. And then 4, we're going to use 3 basically to prove that integral closures are integrally closed. So it's kind of a... Okay, that was weird. Integral closures are integrally closed. Kind of a weird statement. So what do I mean by this? I mean, if you take like your ring of integers in your favorite number field, that's actually an integrally closed ring. So at this moment, we don't actually know that, that I can't just keep taking integral closures over and over again. Basically, that after taking one integral closure, the collection of elements in so what does this imply? What is useful about this? If, let's say I was a number field, and alpha in L is integral over the ring of integers O sub L, then alpha is in O sub L, actually. Okay. In particular, if I'm integral over the ring of integers, then I'm actually integral over Z. Okay, so that's kind of the content of 4 here. Okay, so there's our overview. So let's go ahead and talk about these different types of definitions. Okay, so this is 15.1. So definitions. Okay, so first let's say what it means for, I guess, I'm going to define everything for integral domains because basically there are certain things that I use, basically some of the previous lemmas that I'm going to use from previous lectures, we only proved in the case of integral domains, and we're really only going to need all this stuff in the case of integral domains, but some of it definitely holds more generally. So I'm going to let A contain in B be an extension of integral domains. Okay. So what does it mean for the extension be finite? So we say the extension is finite if, so when do we say this? If B is a finitely generated A module. B finitely generated so this inclusion of A into B gives B the structure of an A module, and if it has finitely generated, or if it has finitely many generators as an A module, then we say this extension is finite. We say the extension is finitely generated or sorry, got ahead of myself. We say the extension is of finite type okay, this is different, and this should be in red. Sorry. What is of finite type if, so instead of being finitely generated as an A module, now we're finitely generated as an A algebra. If B is finitely generated okay, so the difference is now should be A algebra. The difference is now that basically I'm allowing products of the generators as well, rather than just A linear combinations. And I'll give an example of differentiating this finite from finite type condition. And finally, we say B is an integral extension of A if every element of B is integral over A. Okay, so these are the three things. We should come up with some examples differentiating these three conditions. So let's think here. So examples So this is 15.2. So example, let's say 1. Let's do an example of a ring that's of finite type but not finite. So we can do something like maybe Q adjoin X. So the ring Q hard brackets X is of finite type over Q. So as an algebra, it's generated by X. So with algebra generator X, but is not a finite extension of Q. How do I know it's not a finite extension of Q? Well, as a vector space over Q, this thing is infinite dimensional. The powers of X are all linearly independent over Q. Okay. Maybe we can come up with an integral extension, which is not a finite extension. Probably the easiest one off the top of my head, the ring Q bar, so the algebraic closure, of Q is integral over Q, but not finite. So I guess there are really two claims hiding in here. The fact that it's integral over Q, well, Q is a field, so integral is equivalent to algebraic, and the algebraic closure, every element of the algebraic closure is algebraic over Q. Okay, how do I tell this isn't finite? Probably the easiest way to tell is that it contains subspaces of any arbitrarily large dimension. So note, for example, maybe Q adjoin, what do I want to say here? This should be easy, but I'm a little afraid to write anything down. Okay, I think these things have dimension. Okay, I don't want to make a mistake here, so let me think about this briefly. Yeah, I think, okay, this should have dimension n. Yeah, this has dimension n, and is a subspace of Q bar. Thus, Q bar over Q cannot be finite dimensional. So it has a subspace of arbitrarily large dimension. Okay. This one is also an example. Q join X is not an integral extension of Q. So let's see here. Neither is it integral. It's because X is not the root of any polynomial over Q, and I'd have to think about this a little bit more. I'm not entirely sure, but I suspect Q bar is not finitely generated as a Q algebra. So this could be wrong, but I suspect Q bar is not a finitely generated Q algebra. Okay. Yeah, it's kind of an interesting question, but I'm not going to think about it now. So these two examples really show you that, these conditions are all somewhat distinct. So what we'll see next is that finite is, in some sense, the strongest condition you could ask for. So if my extension is finite, then it's necessarily of finite type and integral. So that's the next proposition. So this should be 15.3 proposition. If A is contained in B, a finite extension of integral domains, then it's necessarily integral and of finite type. And then it is of finite type and integral. Okay. So let's go ahead and prove this. And yeah, so it turns out this is going to be an if and only if. This direction is a little bit easier than the other direction. So we'll prove this direction first. The fact that B is of finite type is pretty easy. Over A simply follows from the fact that if I take generators follows from the fact that generators for B as an A module will work as generators for B as an A algebra. Okay, so one way to think about this is A module, or being finitely generated as an A module basically says that every element in B is a linear combination of an A-linear combination of some elements in B, some like fixed finite list of elements in B. And these being of finite type means that every element in B is not just an A-linear combination, but a polynomial, like with coefficients in A in these fixed finite elements in B. So basically, being a finite extension is strictly stronger than being of finite type. Okay. So next we show that every element of B is integral over A. Okay, how do we do this? The main tool is going to be a result we proved in lecture 11. So we need the following from lecture 11. Okay, and this result says, let A be an integral domain an L field containing A. then alpha and L is integral over A if and only if there exists a finitely generated A module M containing L such that alpha times M is contained in M. Okay. So just to briefly remind you how we prove this, you essentially use the generators to write down some matrix, and you use Cramer's rule to show that the determinant of this matrix is 0, and it turns out the determinant of this matrix gives you some polynomial that alpha is a root of. So the key is Cramer's rule, essentially. And if you want to see the proof in more detail, see lecture 11. How do you apply that to prove proposition 15.3? To apply, so A is just going to be A. L is going to be the fraction field of B. And M is going to be B itself. Okay. Then, for any alpha in B, alpha times B is contained in B. And since by hypothesis B is finitely generated A module, we conclude that since B is a finitely generated A module, we conclude alpha is integral. Okay. So every element of B is integral over A, therefore this is an integral extension of rings as well. So you may ask, why was I careful to make these things integral domains? This lemma right here is the main thing. If B is not an integral domain, I cannot take. It doesn't make sense to take the field of fractions. You need an integral domain to form field of fractions. And if A is not an integral domain, well, I can't even state this. Can't even use this lemma as stated. So I really do need, if I want to use this result to prove this, I need integral domain. Okay. So next, I basically want to prove the converse. So 15.4, this is going to be the converse proposition. So now I'm going to take an integral extension of finite type. So let A, B be integral domains. A is contained in B, an integral extension of finite type. And what we're going to prove, then A contained in B is finite. Okay, so I'm going to prove that B has a finite list of A module generators. Okay, let's go ahead and get into the proof. So essentially we're going to prove this by induction. So we prove this by induction. On the number of algebraic generators. of b. Okay, so first, let's consider the base case. In this case, B just has one algebra generator, let's say B1, and it looks like basically polynomials with coefficients in A in this element B1. Okay. So since B1 is integral over A, I can find some polynomial with coefficients in A that has B1 as a root. Some relation B1 to the n plus A sub n minus 1, B1 to the n minus 1 plus A naught equals 0. All these AI's are in A. Okay, so now I claim that we can take as a list of generators 1, B1, so on and so forth, B1 to the n minus 1, generate B as an A module. Okay, so again, we're going to end up doing some kind of induction argument. So first, note that B is generated by all the powers of B1 as an A module. Okay, so this is an infinite list as it stands. However, it turns out that many of these terms are redundant. So thus, it suffices to show so B1 to the n is in the A algebra generated, or the A module generated by 1, B1, B1 to the n minus 1. And here this, I mean, the A module spanned by B1, 1, B1. Okay, so if I can show every power of B1 is in there, then all of B will be contained in this span. Okay, so again we're going to do induction. So this is kind of like a nested induction process, and we're going to do induction on this big N. We see that it clearly holds for n equals 0. Since 1 is in this thing. Okay, and let's say, suppose we know it holds for, let's say, big N minus 1, and consider N. Well, if 1 to the n, if this equals alpha to the n minus 1, b1 to the n minus 1, so on, then what can I say? Sorry. If B and B, so I know B1 can be written as some A linear combination, like this. I can multiply this whole thing by B1. I'll get B1 to the n equals alpha to the n minus 1, B1 to the n plus alpha naught B1. And using the fact that, so using this equation up here, I can rewrite B1 to the n as negative all this stuff. Okay, so this is going to be alpha to the n minus 1 times negative a n minus 1 b1 to the n minus 1 minus a naught. So I'm just replacing b1 to the power n by negative all that stuff, and then I'm still going to get all this alpha naught b1. And it turns out that this is, just by looking at what terms we have going on here, this is in this correct A module. So notice that, so for example, everything here is an A linear combination of B1 to the n minus 1 or less. Multiply this by A, we're still in this A module, and all these lower terms have B1 to the power n minus 1 or less. Okay, so what does this prove? Thus, B equals A join B1 is a finitely generated A module. Okay, so this is kind of the base case of our induction. To prove the induction step, you basically just use, so to prove the induction step, suppose we know the result when B equals A join, let's say B1 through Bn minus B little n minus 1, then if B is now generated by little n elements, this is just this, but with one other generator. So note, by induction, this thing is a finite extension, A contained in B1, Bn minus 1. This extension is finite. By induction, this containment I guess I should make a remark here. This is a integral of finite type extension. So this extension is generated as an algebra by B sub n, and it's integral because everything here is integral over A, so it's definitely integral over here. This implies this extension is finite by the base case. Okay, so I've got a finite extension here and a finite extension here, and this is B. So by the transitivity of finite extensions, so this is something we proved probably in that same lecture, see lecture 11. By the transitivity of finite extensions, B is a finite extension of A. Okay. So let's do a brief recap of this proof of proposition 15.4. So proposition says if I have an integral extension of finite type, and it's actually just a finite extension of rings. The way you prove this is first consider the case when you just have one generator as an algebra. Then you kind of just you use your polynomial relation to essentially reduce the power of b sub 1. That's the way probably I'd like to think about it, is like I take a big power, b1 to the n, and I can reduce this power using this relation until I get down to like the degree of this minimal polynomial or something like that. Okay, so that's how you prove when you have one generator. To prove the result when you have many generators, you just break it up into a bunch of extensions, each of which are one generator over the last, and then by induction, essentially, each of these extensions is finite, and then by transitivity of finite extensions, the whole big extension is finite. Okay. Okay, so there's that. So what is the... So I guess there are a couple questions. One is, why is this result useful? Why do we care about something like this? And number 3, the first thing I want to talk about a couple corollaries. So corollary. So we can prove that finite extensions are transitive just using basically like the very definition. Like if you have a basis for one and a basis for the other, it's really easy to write down. Like the product of the two bases will be a basis for the big extension. Showing that integral extensions are transitive turns out to be a little bit more work. So we're going to let A be contained in B, be contained in C, be integral domains. If B is integral over A, and C is integral over B, what can I say? Then C is integral over A. Okay. So the idea here is that basically this may not be, so like for example, A contained in B may not be a finite extension, but if I fix a B, then A adjoin B will be a finite extension of A, and then I can kind of use some of the stuff from above. Okay, so I'm going to let gamma be in C, and let's say I can find some polynomial in B that it satisfies. Let's say gamma to the n plus b1 gamma to the n minus 1 plus b. I've screwed up the indexing. It should be this, and this should be 0. Suppose it satisfies that polynomial with coefficients in B. Okay. And I'm going to let B prime, this is just going to be the A algebra generated by B1 through Bn minus 1. Okay. By our previous corollary, or by proposition 15.4, right? This is every element here is integral over A, and it's finitely generated as an algebra. B prime is a finite extension of B prime is a finite extension of A, since it is integral and of finite type. Okay. Now what does that tell me? Well, note that the following. So what happens when I do B prime and join gamma? This is a finitely generated. Okay, so I'm going to apply proposition 15.4 again. This is a finite extension of B prime. Why is this? By 15.4 again. Okay, so you can, if this is unclear why I'm applying 15.4 again, I would think about it. If you can understand this application, then you should be able to understand this application. So what does this mean? I've got basically a sequence of finite extensions. Thus, we have A is contained in B prime, is contained in B prime and join gamma, each of which are finite. Okay, so what does that tell me? Transitivity of finite extensions. Thus, A over B prime adjoin gamma is a finite extension. Okay, what else can I say here? Note also that gamma times B prime adjoin gamma is contained in B prime adjoin gamma. Okay, and what do we see here? We see that we can apply this proposition from lecture 11. So, thus, using our main result from lecture 11. So this is this is why I started numbering the propositions. Is I realized that referencing these propositions by things like main result is a little vague. What I mean in this instance is this. This is what I mean by my main result from lecture 11. Or I guess maybe I should say main tool. But using this idea that I need a finitely generated A module so that alpha times M is contained in M. Lecture 11. We see gamma is integral over A. Okay, so I took a random element of C and showed that it is necessarily integral over A. Okay, and there's one last corollary, which is this fourth thing that I wanted to talk about. 15.6 corollary. So this corollary is a little easier, or like follows almost immediately from 15.5. And what does it say? It says the integral closure of an integral domain A in a field L is integrally closed. Okay, so proof. Let B be the integral closure of A and L, and let's say C is the integral closure of B and L. can I say? Well, by the transitivity, A is integral in B and B is integral in C, so A is integral in C. Integral, so C is necessarily a subset of B because B consists of all the elements of L, integral over A. Thus, B equals C. And B is integrally closed. Okay, so this tells us that all our rings of integers are integrally closed in their respective number fields. So this is a useful result. Okay, so I think that about wraps it up for this lecture, and I'll see you next time.